Hi, I'm Zor. Welcome to Unizor Education. So we continue talking about variation of functionals, and today we will consider a very simple problem. Now, this lecture is part of the course called Physics Plus for All. It's part of the Unizor.com website. The website is totally free. There are no advertisements. Sign in is optional, so basically it's completely free knowledge. There is a prerequisite course for this, which is called Physics for Teens, and the prerequisite to that are Math for Teens and Math for All, Math Plus for All. So we also have some other courses on this website, like Relativity for All and some others. Okay, so I do recommend you to watch this lecture from the website, from unizor.com. If you found it on YouTube or somewhere else, it will be just lecture by itself. In reality, this is part of the course. So you really have to take the course, because there is always dependency between different lectures. So this lecture depends on the previous one, the previous depends on the previous to that one, etc. On the website, everything is just structured as separate courses: Math for Teens, Math Plus, Physics for Teens, Physics Plus, Relativity, etc. All right, so let's back to a very, very simple problem, which we are going to solve using a general approach to variation of functionals. So let me just in a couple of words remind you that the functional is a function of a function. An example which we will consider today is the following. Let's say you have the plane with Cartesian coordinates x and y, and you have 2 points A and B where you consider all the functions nice functions, smooth functions. At least second derivative should exist. Now I would like to fix 2 points here. This is A and this is B, and consider all the different functions. These are graphs of all the functions between these 2 points, between points A and B, capital B. I would like to know the lengths of this curve, or of the function f of x. Well, obviously not for all of them, but I would like to minimize this length. So which function delivers the minimum distance between these 2 points? Well, obviously we all know that this is a straight line, right? You know it from geometry. Well, okay, I understand, but in geometry we did not really prove it for like any function. What if you have something really like a curve very close to the straight line, which delivers the length which is less than that? Well, we know it's not. However, it would be nice to prove it in a relatively rigorous way. And relatively rigorous way means that we are supposed to consider all the different functions which connect these 2 points, and among them find the one with the minimum length. Now, how do we approach it? Well, first of all, let's just state that length of the curve, which represents the graph of the function f of x, is a functional, because every function in this class of the functions which connect these 2 points, every function is mapped into some number, which is the length of the graph of this function. So this is the functional. So we're talking about functional phi of f of x. And this is the length of the curve of the function f of x, and we know that the function is supposed to connect these points. So the class of the function which we are considering is this. So all the functions which correspond to these 2 conditions, that it connects points AA and BP, are considered And obviously, again, as I was saying, if we are doing something like a derivative or something, we assume that the function is smooth enough to take the derivative. So all the smooth functions which connect these 2 points, and functional is the length of the curve between these 2 points. And we have to minimize it. Well, let's do exactly what we did when we were considering this as a pure theory, so to speak. Now, all the functions represent certain space of the functions. Now we assume that the function f0 of x is the one which delivers the minimum length. Okay. What do we do next? Well, we find some shift from this function to another function, the function f1, let's say, at x. And we construct the equation of some parameter t, and we consider all these functions. If t is equal to 0, now this is, let's call it g of x of t. Now all these functions are parameterized with the parameter t. At t is equal to 0, we have g is equal to f0. If t is equal to 1, that would be f1 minus f0 plus f0, so it will be f1. So if you consider function f0 and f1 as points in some kind of infinitely dimensional space of all the functions, this represents basically a straight line between these, and for every value of t, this function is either here. When t is equal to 0, this g would be here, and then it would be closer and closer to f1, and the t is equal to 1, it will be f1. So these represents all the different functions between f0 and f1. What do we do next? Well, if f0 is really a true minimum, the value of functional for the functional f5. So the value of the functional of f1 should be always greater, which means this is a minimum by t. So what we do differentiation by t of g of x t. Then what we do? Well, we have to really consider what is the derivative of this at this particular point, which we are assuming is the minimum. So we put it at t is equal to 0, and that would be function of f0 and f1, and now it's supposed to be equal to 0 for any f1. So no matter from where we approach function f0, so f1 can be anything in the neighborhood, but no matter what, for every f1 is supposed to be equal to 0, and that gives a condition on f1. Alright, so this is the plan. And we did discuss it in the previous lecture. I was just kind of repeating this thing. Alright, so let's just go by the book. The only thing is, I would like to make it as delta of x function. So it would be f of 0 of x plus t delta of x. It's just shorter. So changing f1 to anything, it's exactly the same as changing delta to anything else. The only condition is, since f1 and f0 should belong to this particular class, now what is the delta of a? Delta of a must be equal to 0, because it's the difference between this function, which at a, lowercase a, gives a, capital A, and this function. So they all belong to the same class. So if the difference at a would be equal to 0, and the delta of b for the same reason would be equal to 0. Okay, now the next thing is, what is the length of the curve which represents the graph of the function f of x? Well, if we will take a very small piece of this curve ds. Now ds square is equal to what? Dx square plus d f of x square, right? That's the Pythagorean theorem. If this is a curve, this is dx, this is d f of x differential, and by the theorem of Pythagorean theorem, the length of this infinitesimal piece of the curve is this particular thing. All right, so what we have to do integral from a to b of ds. That's our s is, right? The total length is integral from a to b of sum of all the different infinitesimal pieces of ds. Each one is calculated based on this, which is what? Integral from a to b. Let's put everything based on dx. Now, what is df of x? This is f derivative of x times gx. This is again something which we know from the calculus. So dx can be taken out, and it would be square root of 1 plus derivative dx. Am I right? So dx square, now this would be f prime square dx square. Dx square goes out of the brackets. In the brackets we will have, in the parentheses we will have 1 plus f prime square f prime square. Now that's correct. And dx goes out of the square root. Okay, so this is the formula, and this is basically our function now of f. For every function f of x, which basically is in this particular class, this is the value of the function now. We have to take its derivative, square, construct this function, have integral, and that's the value of the function of f. And we have to minimize it. We have to minimize it. Okay, so again, let's do exactly by the book. First, we have to construct this function. Okay, we don't need this anymore. So we have to construct this function and take the function now of gt of x. What is it equal to? Well, instead of f, we have to put the whole thing, this one. Assuming that f0 is our minimum, which we want to find out, t would be a parameter, and delta would be an increment, which eventually we should consider it can be anything, any kind of an increment. Alright, so it will be integral from a to b, square root of 1 plus, so instead of f prime, derivative of f, we have to put derivative of g of x. Derivative means by x, obviously. T is a parameter. So it would be 1 plus f0 prime plus t delta prime square root and dx. So prime of fx, I would change to prime of g. G is this. Since g is sum of these functions, derivative would be sum of derivatives. T is a parameter, we don't touch it. And integration by x from a to b. Okay. So we have to minimize this functional, and again, the approach we take is the following. For any fixed delta, for any fixed increment from f0 to f1, we have to minimize it by t, and that would be the derivative by direction. So it's a directional derivative in the direction from f0 to f1. Okay, so let's take a derivative by t. Now, derivative of integral by x and derivative by t, they are completely independent. Integral is basically an infinite sum, and derivative of sum is equal to sum of derivative. But considering we are doing integration by x and derivative by t, we can interchange it. So instead of doing derivative of integral, I can take integral of derivative by t. And derivative by t under integral would be what? This is to the power of 1 second in the power of 1/2. So that would be 1 over 2 roots. 2 square roots of 1 plus f0 plus t delta square under the square root, multiplied by derivative of inner function of t, which is, this is the power, so it's 2 f0 plus t delta derivative to the first power of 2, so it's 2 times this, times derivative of again inner function is delta prime dx. Okay, so I took a derivative by t of the function under integral. Derivative of square root, that's 1 over 2 square roots, times inner function derivative, which is, this is sum derivative of 1 is 0, derivative of something to the power of 2 is 2 times something, and again inner function is multiplication t by something, so the first derivative would be just that something, some multiplier. Okay, this is a derivative by t. Okay, that's great. And what's next? Next is next is something which I would like to change it a little bit. Now, how do I change it? Here it is. And this will be some kind of a approach which we will continue doing in some other problems. Consider this. This is a very important thing. Integral of u dv is equal to uv minus integral of v du. Remember integration by parts? Formula from the calculus, integration by parts. I'll just use it. I'm not going to prove anything, etc. I consider people do know the calculus. Now, what this is, it's a derivative of some, delta is some function of x. So we have a derivative of this times dx. What is it? That's basically a differential of delta of x, right? Again, back to calculus. Differential of function is derivative times differential of argument. I'll use it, and this would be my d delta, and this would be everything else. So, which means I can actually write the following. This is equal to, so this is u and this is dv. This is u times v, which is, I will put this for the whole thing. This is my v. No, this is my u, sorry. I don't want to write it down because it will be 0. Times v. So v is my delta, because this is d delta. So this is u, and this is d delta. So it's u times delta minus integral of delta times du. And u will be all these things. Integral from a to b, obviously. Now look at this. Delta is, so I have to put this from a to b, right? Which I did not put at a to b. The value of b minus value of a. Since a and b are 0 for a delta, the whole thing goes to 0. And what remains is this one. Okay? So what remains is, let me just use my formula here. It would be integral of delta times differential of this thing, right? From a to b. And that with a minus sign, by the way. It was a minus sign here. Okay, I don't need any more. So this is a very important piece. I use this integration by parts to get rid of something which is very, very important, because it's equal to 0. And this one would be much easier to deal with, regardless of the fact that this is a differential of this, which means this is equal to integral of delta times, I have to really take what is differential of function. Now, by the way, 2 can be cancelled. It would be f0 prime plus t times delta prime divided by square root of 1 plus f0 prime plus t delta prime square and square root and dx and derivative. So instead of differential by this function, I use derivative of this function times differential of argument. Again, same thing. du is equal to u prime times dx, where u is any function of x. Okay, that's actually almost everything, almost ready. This is, sorry, with a minus sign. Okay, so this is a derivative by t. So it's a derivative along certain direction. It's a directional derivative from f0 to f1, which is f0 plus delta. Okay, now we assume that f0 is the point of the minimum, right? Which means that this derivative by t at point f0, so let's say, if you remember, I was talking about two-dimensional function. Instead of functionals, I was using in the previous lecture analogy with the function which depends on two arguments. So you can assume that this is point of minimum. So no matter where you shift from this point of minimum, as soon as you go along this line or this line or this line or any other line as a function of parameter t, this is supposed to be at this particular point, which means at t is equal to 0. Remember, my gt of x is f0 plus t times f1 minus f0. This is delta. So at t is equal to 0, it's equal to f0. So we need not just any kind of derivative. We really have to check that this derivative is supposed to be equal to 0 at point f0, which means at point t is equal to 0. So this derivative by t, if we want to know what is the value of this derivative at point f0, we really should see how it is at t is equal to 0. Well, let's just substitute t equal to 0. We will have integral from f0, this don't need anymore, square root of 1 plus f0 square, right, dx. That's what this derivative is at point f0 when t is equal to 0. And at point 0, times delta. And what's important is it's supposed to be 0 for any kind of delta. So any increment from f0 to any other side must actually result in this derivative to be equal to 0. When is it possible? Well, if it's for any delta as a function, now this must be equal to 0. Otherwise, integral can always be, if this is not equal to 0, if this function is not equal to 0, I can always, I forgot to put another prime, sorry. Prime, this one, and then delta dx. So if this is not equal to 0, any function, if it's not equal to 0, something like this, I can always find some interval where it's really far from 0, and have the function delta also something similar to this, and their integral, their multiplication, the result of their multiplication will not be equal to 0. So my function must be equal to 0, this one, under integral, if its product with any other function is integral is equal to 0. It's a very easy thing to basically prove, but I think it's kind of obvious. And again, the way how to prove it is just basically assume that this is not equal to 0 within certain area, and then construct the delta such that it's equal to basically something like 1 around this area, and then whatever else somewhere else. So that would be very easy to prove. Okay, which means this is supposed to be 0, and this is a derivative, which means what? Which means whatever is under derivative must be constant. Now, if my f0 prime divided by square root of 1 plus f0 prime square is constant, what does it mean? It means that f prime is constant of x, right? Otherwise f0. So if this is constant, it means f0 prime is supposed to be constant, which means f0 of x is linear function of x, right? If the derivative is constant, this is integral of the constant, which means linear function, something like px plus q. So f0 must be linear function. Well, and considering we have two conditions where this linear function is supposed to go through, that's obviously a straight line between AA and BB. And if you want to have an equation which basically gives you the equation of the straight line between these two, you just have to solve P A plus Q is equal to capital A, PB plus Q is equal to lowercase b, to uppercase B, and the result would be f0 of x is equal to a plus 1 over b minus a, and we will have b minus a times x minus a. So this is the result. If x is equal to lowercase a, the whole thing is 0, so we will have capital A. And if x is equal to b, that would be b minus a divided by b minus a. So I will have only capital B minus a and a cancel, and I will have only b. So that equation. So this is the result. We found the function f0 which minimizes this function, minimizes the lengths, and this is a straight line. Basically, it's a proof, if you wish. I mean, there are some other difficulties to say that this is a proof, because we were using the Pythagorean theorem in the very first place, which is kind of very, very far from the beginning of geometry. But in any case, so I do recommend you to read the notes for this book, so you go for this lecture. So you go to unizor.com, choose this particular course, go to chapter called Variations, and this is the problem number 1 in the variations. Okay, that's it for today. Thank you very much and good luck.